Hello, my name is Mohammed Yousefi, a current graduate student at the University of New Mexico, and in this talk, I will present our work done in deep prediction of swept volume geometries, robots, and resolutions.
So what is swept volume? Swept volume of an object in motion is the space occupied by the object body at any point during its motion trajectory. This swept volume indicates a region where the object can collide with its environment and is useful in planning applications. For example, in motion planning applications, swept volumes can be checked directly for collision and determine the feasibility of a path. In task planning applications, swept volumes can be used as representations of the tasks and determine the order of the tasks to complete without interference. One of the obstacles to using swept volumes is the high computational cost, and generally speaking, exact computation of swept volumes is not feasible. Because of this, many applications use approximation of swept volumes to allow computation in a reasonable time. There are primarily three categories of swept volume approximations: boundary-based, convex polyhedra-based, and occupation grid-based methods. Boundary-based methods compute the swept volume for only the contributing surfaces of the object. Convex polyhedra-based methods determine convex enclosures for the object which have reduced complexity. Occupation grid-based methods discretize the space to reduce the complexity of the problem. Still, these approximations become increasingly expensive as the complexity of the model increases, such as is the case with manipulator arms. In our work, we chose a learning approach with deep neural networks instead of iterative generation to speed up the process. The network we use learns the swept volume problem as a classification task and approximates swept volume directly from the configurations of the robot. To do this, we first define a grid, where each position in the grid is uniquely identifiable by its location along the three-dimensional axes. The network must then learn the properties of these grids and classify each location as occupied or unoccupied given the configurations of the robot. We believe that this is possible since neural networks are known to be good classifiers. Next, I will show you the structure of the network. It is a feed-forward network with fully connected layers that is similar in shape to decoder networks. Decoder networks generate high-dimensional output from a small set of expressive features. In our model, the inputs are a small set of joint positions, namely the initial pose and the final pose joint positions for the robots. The outputs are a set of non-negative values which represent the grid space for the robots. The dimension of the output layer is equivalent to the width times the height times the depth of the grid. We generated the ground truth using an iterative generator in a simulator. We use standard mean square loss to train the network and found that the network works for a multitude of robots with this simple structure. The robots we use are a set of robots which include some real and some models we made for experimental purposes. The KUKA, Baxter, Sawyer, UR, and Micro robots are all real robots used in industrial or educational settings. The planar robot is a model we produced with 16 rotational joints to represent a high degree of freedom robot. The closed-loop robot, represented by CL, is a robot with two fixed bases and kinematic constraints. The prismatic robot, noted as PR, is a robot which has sliding joints in addition to rotating ones. The white cubes in the figures are cubes with a dimension of 10 centimeters representing the grid space compared to the robot's size. The small extra cube in the figure for the KUKA robot is the resolution of the grid at 2.5 centimeters. Next, I will show the experimental results. Our experiment shows that the networks are capable of learning the swept volume. Here in this video, you can see the configurations for the robot on the left-hand side. The blue figure in the middle represents the ground truth, while the red figure in the middle represents the prediction by the network. The error for the prediction of the sample is shown within the grid space represented by the yellow box on the right-hand side. The two samples shown here are for the KUKA robot at a resolution of 10 centimeters and 2.5 centimeters, respectively. But how good are these predictions? To quantify the success of this network, we first analyze its accuracy. Recall that the network outputs non-negative values. We apply a threshold to these values and consider values above the threshold as occupied and otherwise as unoccupied within the grid. We see that the accuracy is high for all robots across multiple threshold values. We believe this to be due to the presence of voxels that are always occupied, for example, those near the base of a robot, and others that are always unoccupied, like the ones that are not reachable by the robot. Because of this, we also look at the F1 score. A F1 score of 1 indicates a perfect prediction by the network. Here, we can better see the effects of the threshold on the F1 score for the network and believe F1 score to be a better indicator for the success of the network. But what is the effect of the threshold on predictions? Here in this plot, we can see the relative error volume when compared to the ground truth. The blue line represents the false positive, while the red line represents the false negative error. The yellow dashed line represents the absolute volumetric error for the predictions. One of the benefits of the threshold is that it allows us to tune the output of the network. In situations when we are interested in taking less risk, we can tune the network towards overestimation, while in situations when we are interested in finding a path despite taking greater risk, we can tune the network towards underestimation of the swept volume. Note that the value of the threshold at the least volumetric error is in the proximity of 0.5, and we use 0.5 for the rest of our experiments. Next, we wanted to analyze the nature of the errors within the network prediction. To do this, we compute the error distance of the falsely predicted voxels. This error distance is simply the Euclidean distance from the false prediction to the nearest voxel in the ground truth with the same label. This allows us to compare the distances to the surface of the swept volume. We use this error distance to characterize the error in the predictions. Using the error distance, we found that most errors are near the surface of the swept volume. In fact, we found a high percentage of the errors within only a distance of 1 voxel from the surface of the swept volume. Although the maximum error distance can be high, we found that for 13 of the robots, almost all of the errors are within a distance of only 3 voxels from the surface, and the errors beyond the distance of 3 accounted for only 0.5% of all errors. The 2 robots that performed the worst in our set, the planar robot and KUKA at 2.5 centimeter, had 77% and 91% of the errors within a distance of 3 voxels, respectively. This shows that the errors are mostly confined near the surface of the volume, and further refinement to the process may allow us to get better predictions of the swept volume. The final result I would like to talk about is the speed of the predictions by the network. The one-time training costs for the networks ranged from minutes to hours. Predicting swept volumes were in the order of milliseconds. Comparatively, generating ground truth by an iterative method in simulation were in the order of a few seconds. This gives an average of about 1,000 times faster than generating the swept volume by simulation. With these speeds, we are likely to be able to use the predictions during online planning. With that, I would like to reiterate some of the discoveries we've made during our experiments. We see that the networks are capable of learning the swept volume for multiple robots and at various resolutions. These predictions are fairly accurate, and the error typically occurs near the surface of the swept volume. We've introduced a tunable bias which can be tuned towards overestimation and underestimation of the swept volume, and we've shown that these networks are about 1,000 times faster than generating swept volumes by simulations. Additionally, 1.5 million data samples are available to download at tapialab.science/resources. Thank you very much for listening,